Assalamualaikum, we are Group 10. Today we present our control system parameter assignment. This project focuses on the analysis of a unity feedback control system. The objective of this assignment to determine the transient response characteristic, analysis the stability, obtain the state space representation, and verify the result using MATLAB and simulate simulation. First, in equation 1, transfer function, we discuss the given transfer function of the system. The gain k is set to 150. After the substitution, the value of transfer function becomes 150 divided by s cubed plus 20s squared plus 85s plus 150. This transfer function is using throughout the analysis and simulation. Next, in equation 2, calculate of peak time, cycle time, and percent overshoot. First, the value of dominant pole and the system parameter we can get from the transfer function, which is S is a pole, omega n, omega t, and theta. After we get the value, we can get the peak time, cycle time, and percent overshoot following the formula.
Hi everyone. After the calculation part, we transition our theoretical third-order transfer function into MATLAB and Simulink to observe its real-world step response. As you can see in our block diagram, we set up a unity feedback loop. We use a step block as our input, fed it into the expanded third-order plant transfer function. And this is our transfer function. After that, we capture the behavior using a scope block. After we simulate this, the scope provides us with some very specific data points. First, for the peak value, we get 0.586, exactly at 0.897 seconds. After that, for settling time, the time taken to reach 2% of our final value is 1.953 seconds. And finally, for our steady state final value, we get 0.5 value. And that brings us to question 4. How does this match our math? When we look at the final value, it's perfect match at 0.5. Our calculated peak time is 0.847 seconds. Was incredibly close to the simulations, which is 0.897 seconds. And that's only about 6% error only. However, our calculated percent overshoot was 12%, while the simulation show roughly 17.21%. So why is the gap? So the reason is the third pole effect. In our manual calculation, we simplified the system by assuming it's pure, dominant, second order approximation. But in reality, this is a third order system with an extra pole at s equal to negative 15. Even though that pole is far to the left, it still exerts a subtle pull on the transition curve, shifting our peak time and increasing the settling time and overshoot in the actual simulation. Ultimately, the simulation validated our second order math can be reliable.
Assalamualaikum. My name is Muhammad Daniel Iman bin Muhammad Zanis and I will present question 5, which is the state space representation. State space representation is a mathematical model used to describe the behavior of a dynamic system using a set of first order differential equations. It represents the system in terms of state variable input, output, and system matrices. For this question, the given transfer function is g of s equal 150 over s cubed plus 20s squared plus 85s plus 150. From this transfer function, we convert it into the state space form. The state variable are defined as x1, x2, and x3, which is represent the output and its first and second derivative. The state space matrices obtained are metric A describe the relationship between the state variable. For metric B, represent the system input. For metric C, represent the system output. And the last one, metric D, is equal to 0 because there is no direct transformation from the input to the output. Therefore, the complete state space model of the given transfer function has been successfully obtained.
Assalamualaikum warahmatullahi wabarakatuh. My name is Salim and I will do the presentation for question 6. And now we will be looking at the stability analysis for a closed loop system to determine if the system is stable with the Routh-Hurwitz criterion. We started with our closed loop characteristic equation with the previously calculated as s cubed plus 20 square plus and 85s plus the 300 equals to 0. From here, we extract the coefficient to build our root array. As you can see on this table that I have done, we fill in the first two rows using the equation coefficient. When we calculate the remaining value for s to the power of 1, this one, s to the power of 1, and s to the power 0, and the calculation gave us values of 70 and 300. The crucial step is evaluating the first column of the array because all the numbers in the first column 1, 20, 70, and 300 are strictly positive and there are zero sign changes. We know there are no poles in the right half of the S-plane. Therefore, we can conclude that our control system is strictly stable. Thank you.
Next, I will explain the steady-state error analysis. For the definition, the steady-state error is a difference between the desired output and the actual output after the system has reached the steady-state condition. For the given unity feedback system, we calculate the steady-state error for three different input signals. For the step input, the position error constant Kp is equal to 1. Therefore, the steady-state error is 0.5. For the ramp input, the velocity error constant Kv is 0. Therefore, the steady-state error is infinity. Last but not least, for the parabolic input, the acceleration error constant Ka is also 0. So, the state error is infinity. From this result, we can conclude that the system is able to respond to a step input with an infinity steady-state error of 0.5, but it cannot accurately track ramp and parabolic input because their steady-state error are infinity. That's all for our group. Thank you for your attention.